In the last lecture, we have studied the relationship between continuous time unit impulse del of t and continuous time unit step function u of t. Okay, so in this lecture, let us understand a little more through an example. Okay, so I am going to consider an example and let us see. So let me draw the function x of t. So the x of t looks like this. It is a continuous time signal. This is 0 up to the point 1. Let's say this is 1, this is 0, minus 1. At 1 it jumps to the unit of, jumps by the unit of 2, and at 2 it again comes down and it goes negative of magnitude 1, and it stays for some time. At t equals 4 it comes up and it goes like this. So this is my x of t. So 1, 2, this point is 3 and this point is 4. Now we would like to find the derivative of x of t. Let me denote the derivative of x of t by x dot of t, where x dot of t is defined as d by dt of x of t. Specifically, the derivatives of x of t is clearly 0 except at discontinuities. Okay, so in this discontinuities, in this constant, the derivative is 0, and here the function is constant of minus 1. This point is minus 1, this point is 1, then the derivative is 0 in this point. Similarly, here also in this region the function is constant, the derivative is 0, and here also the function is constant, therefore the derivative of x of t is 0. Okay, so at continuous points, here I have the derivative in this point. So these are the only 3 places I will get x dot of t is not equal to 0, and here also the derivative of x of t is not equal to 0, and in this point also I will get which is not equal to 0. Okay, so in the case of unit step, we proved the relation that del of t is equal to d by dt of u of t. When you differentiate a unit step function like this, then you will get an unit impulse. So this is a height of 1 unit, so I will get a height of 1 unit here. Okay, so therefore the differentiation of unit impulse gives rise to a the differentiation of a unit step function u of t gives rise to a unit impulse function del of t. If the rise is at t equal to 0, then I will get del of t. If the jump is at t is equal to 1, then I will get del of t minus 1. If the jump is at t equal to 2, let's say u of t minus 2, then I will get the impulse sitting at del of t minus 2, and so on and so forth. Therefore, wherever you find the discontinuity, there you will get an impulse function if you differentiate. Okay, so this is u of t minus 1. If you differentiate, you will get del of t minus 1, because there is a discontinuity at t equals 0. And here the discontinuity occurs at t equals 0. Therefore, you got del of t. And in this point, there is a discontinuity. and this discontinuity occurs at t equals 2. Therefore, you will get del of t minus 2 and so on and so forth. Now, if you come to this function, now if I try to plot the derivative of x of t, it is 0 up to this point. This is a 0th point. In this, sorry, up to this point, this is 1. At 1 there is a jump, and that jump is by 2 units. Okay. This is maybe 1 minute. This is not clear. Let me go down little. Okay, so like this, 0 1. When you come to 1, when you come up to this point, then there is a jump. This jump is by 2 units. Therefore, you put an impulse by 2 units. So that area under the impulse is 2 units. So there is an impulse at a t equals 1. Fine. Now again the function is constant in between 1 and 2. So it is 0 here, and when you come to this point, then there is a jump of minus 3 units. Okay, discontinuity of minus 3 at t equals, when t equals 2, then there is a discontinuity. Okay, the size of the discontinuity is 2 minus 3, because this point is 2 and this point is minus 1. Therefore, it is coming down by minus 3 units, so that an impulse scaled by minus 3 units. So this is minus 3. And again, in this point it is constant. Again there is a jump by 2 units plus 2 units at t equals 4. So this point is t equals 4. So 2, 3 and 4. At t equals 4, there is a impulse of 2 units. So this is your x dot of t, this one. So from given signal x of t, I got x of t, x dot of t, where x dot of t we defined as first derivative of x of t. Now one can ask a question: can we get back my x of t from the derivative of x of t? That is one need to check. As a check of our result, we can verify that we can we recover x of t from x dot of t. That is one need to ask. So that we know that from impulse function to unit step function, the answer is u of t is equal to integral of, let me write down somewhere else here, u of t is equal to minus infinity to t del of tau times d tau. Similarly, if you want x of t, then integrate x dot of t, x dot of tau d tau, then minus infinity to plus infinity, or whatever it is. Now I am going to take this function and do the integration. Okay, so region by region you can do this integration. You can first consider one region and then do the integration, and then consider the second region. Okay, first let me consider t less than 0. Okay, when I consider t less than 0, the integral is x of t is integral of 0 to t x dot of t and let's say x dot of tau d tau, like this. When you consider t less than 0, then what will happen? None of the impulse present, okay? None of the impulses that constitute x dot of t are within the interval of integration. Therefore, when t is less than 1, it is not 0, it is 1. When t is less than 1, then this integration would lead to 0. Okay, so let me make this place very clear so that I can draw here. Fine. So when t less than, sorry, not 0, it is less than 1, then integral of 0 to 1 x dot of t tau d tau. So if we consider the derivative up to this point, there is no impulses. So therefore 0 to 1 x dot of tau is 0, 0 times d tau, it is equal to 0. Therefore the function is this is x of t constructing from x dot of t by integration. So this is 0 up to this point. Okay, up to 1 it is 0. This is 0, minus 1, minus 2, this is 1, right? Because it doesn't contain any impulse. Now let me take the second interval, let's say 1 to 2. T lies between 1 and 2. In this region, if you look at from 1 to 2, from this point to this point, then it comprises the first impulse, because the first impulse is located at t equals 1. Therefore 1 to 2. So let's say 2 minus, I am not going to consider this impulse, I am going to consider this impulse alone. So x dot of tau d tau. Okay, so the first impulse is located at t equals 1, is the only one within the integration interval. Therefore this is going to be 1 to 2. What is the height of that impulse? 2. 2 times del of tau. No, that impulse is located at tau minus 1. So d tau. Now this 2 is constant, you can pull out of the integration. 1 to 2 del of tau minus 1 times d tau. So this integration area is equal to 1. Therefore it is 2. So in the interval 1 to 2, my area is 2. So from 1 to 2, the area is 2 units, like this. So this is 2. That's it. 2 constant, it is constant between 1 and 2. Fine. Now let me consider the third interval from, let's say, 2 to 4. So the first integral leads to the area of 2 units. Now if I consider 2 to 4, like where t lies between 2 and 4. Now in this 2 and 4, you have this impulse. okay, of the strength of minus 3. Therefore the integral is minus no, not minus, 2 to 4 x dot of tau d tau. So this is going to be 2 to 4. In that the derivative is this function, so minus 3 times del of the delta function is located at t equals 2. So therefore tau minus 2 d tau. Now that 3 can take outside, minus 3 times integral of 2 to 4 del of tau minus 2 times d tau, and again the area is equal to 1. So therefore this integration is equal to minus 3. Okay, so if you sum both of their areas, see this area is 2, height is 2, and here this area is minus 3. If you sum these two, that's what you are going to get from this point onwards. That is equal to minus 1, because total area is equal to, see, total integration length is from here to here, minus infinity to 4. This minus infinity to 4 we break into minus infinity to 0 and 0 to 1, sorry, minus infinity to 1, then 1 to 2, then 2 to 4. So minus infinity to 1 the area is 0, 1 to 2 the area is 2 units, and 2 to 4 we got minus 3. So what is the total area now? Total area is 0 plus 2 minus 3, which is equal to minus 1. So in this point I have minus 1. Okay, so that is where what we got here, minus 1. Here also you have minus 1. Minus 1, fine. Then take the next interval, finally t greater than 4. So if you consider t greater than 4, because I need the space, so I am deleting this. If you consider t greater than 4, then what will happen? Your all three impulses will come in this region. Okay, so all three impulses are within the integration interval. When t greater than 4, then you have the integration of minus infinity to 1, right? X dot of tau d tau plus integral of 1 to 2 x dot of tau d tau plus 2 to 4 x dot of tau d tau plus 4 to infinity x dot of tau d tau. So these are the different integrals. You can split like that. And anyway this guy is going to give 0, but if you look at the figure up to 1, the derivative is 0. So the first integral is 0, and the second integral we found, that is going to be 2 units. Okay, then this third integral we found minus 3 units, and the last integral is going to be 4 to infinity x dot of tau into d tau. So in that case it includes this unit impulse function. Okay, that 2 times of that function. Therefore 2 times that impulse function. How do you describe mathematically? Del of t minus, it is located at 4, t equals 4, therefore del of t minus 4. So you substitute here del of tau minus 4. It's a dummy variable, that's it, d tau. So which is equal to 2 minus 3 becomes minus 1 plus 2 times integral of del of tau minus 4 and d tau. Again this is 4 to infinity. So the area under this impulse function del of tau minus 4 is going to be 1. So minus 1 plus 2, which is equal to 1. So when t greater than 4, the x of t is equal to 4 units. Therefore this point is 4 and this is 3. When t greater than 4, then it looks like this. That's all. Okay, that's how you will calculate the x of t from x data of derivative of x of t. So that's how the relation goes between x of t and x data x dot of t, that means d by dx of t. So that means what we trying to say is you have three impulses. One is located at t is equal to 1 with magnitude of 2 units, and another one is located at let's say 3 units. This is 1 and this is 2, and then you have one more impulse at 4, and the impulse strength is again 2 units. So these are the three impulses. Time axis minus infinity. Now what you do is you integrate from this range when t less than 1. If t less than 1, by the way, this is your x dot of t, derivative of x of t. Now in this region minus infinity to 1, x dot of tau d tau is equal to 0, because the function is 0 up to here. Okay, so therefore if you integrate, then you will get x of t. Therefore the first thing is x of t is equal to 0 if t is less than 1. So this is the first condition we got now. Now what is the second one? You consider t which lies between 1 and 2. Okay, so in 1 and 2, your x of t is going to be integral of 1 to 2 x dot of tau d tau. Now this integral comprises this delta function 1 to 2. Therefore you consider here. So this is equal to 1 to 2, and this impulse function, how do you describe? 2 times del of t minus 1. So 2 times del of t minus 1. So you take 2 outside, tau minus 1 d tau. So 2 times, again this area under this function is 1 if you take 2 outside. So this is 2 units. So x of t is equal to 2. Let me write down here. X of t is equal to 2 if t is between 1 and 2. So this is another t. Okay, so or else you can say, yeah, that's okay, fine. Now let us consider another interval. Like as I said, 2 to 4. Similarly, you can work on it. 2 to 4. Okay, 2 to 4, again you put 2 to 4 x of t is equal to x dot of tau d tau. Okay, so in this interval, this impulse is located with the impulse strength of -3. So minus 3 times del of, it is located at t equals 2. Therefore tau minus 2 d tau. You pull out this outside, minus 3 times del of tau minus 2 d tau, and this is going to yield 1. So therefore this is minus 3. Now I cannot write x of t is equal to minus 3 in this region, because I will tell you 2 less than t less than 4, like this you cannot write. This is wrong. Why is it wrong? Because when you consider the function x of t is, no, in this interval it is correct, but when you consider on the whole, you are accumulating, right? So x of t is accumulating the area, right from minus infinity minus infinity to the point where you want. Therefore, I cannot say like this. Therefore, whenever I want to write, then I have to add all the areas. Therefore, x of t is equal to 0 plus 2 minus 3. Then I should write t less than or 4. Therefore, this is minus 1. Why? By original definition, your x of t is integral of minus infinity to t. But again, piecewise it is varying. That's why we are considering this interval. So, x dot of tau d tau. That is why this is minus 1. Okay. Now, see, now you can do one more time and then you can plot. So, the plot looks like this. Up to t equal to 1, it is 0, and when between 1 and 2, its height is 2. Then between 2 and 4, its height is minus 1. Then again between 4 afterwards, it is plus 1. It keep on goes, so that you will get back your original signal x of t from x dot of t by integrating. So, this is x of t and this is 2 units minus 1 plus 1, that's it. Okay, so let me stop at this point. So, we have gone through the relationship between the unit step function and unit impulse function through this example. Thank you.